My name is Thomas David. I'm a research associate at the University of Bristol, and I'm going to present my project, which is about enabling the automated assessment of precision aerobatic manoeuvres. Precision aerobatics is a competition discipline for full-size and model planes. The picture on the right shows a typical scene at an RC aerobatic competition with the pilot standing at the front and a line of judges sitting behind. The pilot is flying manoeuvres on a vertical plane about 200 metres away, and the judges are looking for perceived errors in the execution of the manoeuvres. Judging is a very difficult job, and it's hard to remain completely objective when you're doing it. The aim of this project is to take off-the-shelf UAV technology and see if we can use it to reduce the subjectivity of the scoring. This picture shows the insides of one of my planes with a Pixhawk flight controller fitted, a GPS and some other bits that you're probably familiar with. The flight controller is working completely separately from the stuff that controls the plane, and it just records the state information listed on the right. Here I have broken the process of post-processing the flight logs up into 5 steps. The first one is to read the flight log. There's a load of open source tools that make it really easy to read an Aerobatics flight log, but if people are going to trust the process that we develop, then it's a really important thing to do, and that is to present the data in a nice way. The screenshot here shows the flight coach plotter, which is a free web app for displaying Aerobatics flight logs in a way that's useful for aerobatics. The recorded flight is shown as a ribbon, and a 3D model of the plane follows a track. You've also got a splitter so you can select individual manoeuvres. We probably have a few hundred people using it regularly from all around the world. For this paper we use PyMavLink to read the flight log, and most of the plots you see, like the one on the right here, are using my PyFlightCoach package, which you'll find on GitHub, and it's got lots of nice tools for post-processing flight logs. The next job is to make a template set of flight data with the same sequence of manoeuvres and with all the same state information as a recorded flight. Aerobatic sequences are drawn in arrestee diagrams. The one on the right here shows a bit of the P23 sequence, which we'll be using in most S3A competitions for the next 2 years. We've split the sequences up into basic building blocks, or we've called them principal elements in the paper, that are joined together to make manoeuvres. I'll talk a bit more about the loop and line principal elements here, as they're the most common ones. This is the line element. We can specify the length of the line and the number of rolls to perform during it. All the principal elements have some kind of scaling parameter. We've defined lots of functions that allow them to be scaled manually or based on measurements of the flight data and so on. Setting rolls on the line superimposes a body frame X rotation on top of it, so it means we can cover the roll element at the same time. This is the loop element. Like the line, we've got a scaling parameter, which is the diameter of the loop, and the number of rolls to superimpose onto it. We've also got a number of loops to perform and a boolean that specifies whether the loop should start at knife edge or not. These pictures show a normal loop and one with a single roll integrated, making a rolling loop. Once we have a recorded log and a template log, we can run a temporal alignment between the two to identify all the manoeuvres and elements in the flown data. So far we've been using dynamic time warping to label the flight log. It seems to work pretty well, but it does depend on the flight being a pretty good one and the template being reasonably similar to the pilot's flying style. I think we can make this step much better in the future by improving the template, by adjusting it to include the wind and angle of attack of the model, and by considering other alignment methods, or maybe a hidden Markov model or a neural network. Once we've found the bit of flight data that represents each primitive element in a sequence, we can rescale the template to match the pilot's intention during the flight. Here's a different manoeuvre from the P23 sequence. The picture shows the recorded data and the rescaled template on top of it. The steps are in the template, and they are there because only the initial position of each element can match between the flown data and the template unless the element was flown perfectly. By aligning the initial positions, we can measure the line length directly, and we can measure the loop diameters by fitting circles. The last step in the process is to compare the template elements to the flown elements. This picture shows a comparison of a flown spin to a template spin. It's a nice example, but we'll carry on looking at loops in more detail. The aim of this project is to enable the automation of judging. We don't want to do the whole thing because there are lots of different competition disciplines and they won't be happy if they don't have control over how their scores are applied. This means it's more important to present the data in a way that makes it easy to calculate scores than it is to actually calculate the scores. Most of the downgrades are either applied at the element level or at the manoeuvre level. You can score the level ones by looking only at mistakes within a single element. For the manoeuvre level ones, you can compare the measurements of the elements that we took when scaling the templates to match the flight. We'll carry on by looking at this 7/8 loop element and how you would score the element level downgrades if you were judging S3A, which is a discipline I compete in. The three graphs on the right show the three main things you need to look at in order to score a loop element, and they're all plotted against the radial position around the loop. The first one shows the loop radius. Most of the deviations are pretty small except at the end where it gets a bit tighter. The rules say a judge should take half a mark for a visible change in radius, so we're down to 9.5 out of 10 for this element. The next graph shows errors in the heading of the velocity vector in the loop axial direction. In S3A you take 1 mark per 15 degrees of error. Here we have 3 separate 7.5 degree deviations worth half a mark each. That puts us down to 8 out of 10. The last graph shows the error in roll angle. Again, this is 1 mark per 15 degrees, so the 15 degree error at the start and the 7.5 degree error at the end take us down to 6.5 out of 10. This is just for one element of the manoeuvre. We still need to score all the other elements and then compare all their sizes to do the manoeuvre level downgrades. For this example, I selected one of my best attempts at this manoeuvre from about 10 flights. If I follow this process through for every element, I'd be lucky if I end up with more than a minimum score of 0 for the manoeuvre. It's worth noting here that I won the British National Championships last year. Clearly, if everyone scores 0 for most of the manoeuvres in a competition, then we won't get a sensible ranking, so you might need to look at weighting the downgrades to make them less harsh when applied automatically. We've shown that UAV technology can be used along with some careful post-processing to enable automatic judging of aerobatic manoeuvres, but the grading criteria may need to be adjusted if we want to get sensible rankings. While we've been working to solve the technical problems, there are still political ones that need to be solved before automatic judging could be used in a competition. It could even be that human judges are just as important to our enjoyment of the competition as the competitors. If you don't fly aerobatics, I hope that you'll still find some of the tools we have developed useful. The Flight Coach Plotter is a good way of visualizing ArduPilot data flash logs, and the Flight Coach Python package has lots of useful tools for analyzing flight data. The processes developed in this paper could also be useful in other areas such as flight regime recognition, pilot training, and control system development. Finally, here is a video recorded from the Flight Coach Plotter showing one of the manoeuvres from the F3A F23 aerobatic sequence. It shows a rolling horizontal figure of 8. The plotter is one of the most important parts of the project. It is essential that any automated assessment method comes with a means of giving pilots feedback alongside their scores. It even opens a possibility of online or postal aerobatic competitions.